the electric field, and therefore its potential here, which as I said is called the scalar potential, because it is a scalar, whereas this one is called the vector potential. That enters the Hamiltonian precisely in the same way as the potential from the nuclear charges. And that is, so the scalar potential enters, all right, as potential energy, which means a potential energy means you have the charges in your system times that potential. So we get a contribution to the Hamiltonian, an extra contribution to the Hamiltonian, well, I could call it already H prime, which is the sum over all charges in my system, just it's QP, times this potential. And the value of the potential at the position of this charge QP. And I mean, this is, as I said, the electron-nuclear interaction term, the electron-nuclear attraction, I can write in the same way. And there the potential is just here now, that would be the charge of the nucleus divided by the distance of the nucleus to the electron I'm looking at, would be the potential there. And then you have to multiply it with the charge of the electron. So in a molecule here, I get now two contributions. I obviously get a sum over all the electrons. And the charge of the electron is minus the elementary charge. So I get sum over minus E, and let's call it E over all electrons, times this potential at the position of electron E. And now I get a positive contribution from, and I can move the, well, I couldn't move the E in front of it. I get a positive contribution from all the nuclei, what do we call them, A, where the charge of the nucleus is the atomic number times the elementary charge. And then again, my potential, and here the value at of the potential at the position of nucleus A. That's sort of the easy part. The sort of bit more unusual part is where does that vector potential enters. And one can derive that with classical mechanics. If one uses this Lagrangian formalism, one can derive how the vector potential should enter the Hamiltonian. I'm not going to do that here. I'll just tell you at the end that it actually enters together with the velocity. If you have charges moving around in a magnetic field, that changes the velocity. So the vector potential enters the Hamiltonian via the canonical momentum, or the, well, not actually the canonical, but the mechanical momentum. The momentum of the electrons or the nuclei, but since we're using Born-Oppenheimer, most of the time for us it's now only the electrons, because normally you have that the momentum of the electrons, of an electron I, the canonical momentum, is the mass times the velocity. And this is the canonical momentum, the one which is then replaced by the gradient operator if you go to classical to quantum mechanics. Now this is now changed. So if we have a vector potential present, and we're talking about electrons, so it comes the vector potential comes in here. So this is called the canonical momentum. Which is the one you normally have in the Schrödinger equation and replaced by, so this is minus I h bar the gradient operator. Whereas this is called either the mechanical momentum or the kinematical momentum, because that's the one which relates to the kinetic energy. Now, if you have a vector potential present, there comes an extra contribution. Because the kinetic energy of an electron in a magnetic field is different than when it would be, and also the velocity is changed. But that means that the kinetic energy term in the Hamiltonian then is going to be changed. So normally for electrons you have 1 over 2 me times the sum over all electrons, and then you would have this canonical momentum operator squared. But now there's an extra contribution from this vector potential, and the kinetic energy operator looks like this now. Now we can expand that in order to see which are really the extra contributions which we get. So what is the H prime? Because that's the full kinetic energy term now for the electrons. So if we expand that, calculate the square, then we get 1 over 2 me, we get the sum of I pi squared, plus 1 over 2 me, and then we get pi, we get an e here, pi times dot a, and the other way around, dot pi plus e squared divided by 2 me times the vector potential squared. Now this part is just our normal kinetic energy operator, which means that all the other parts, those are extra terms when we have the field. So those are sort of our perturbation Hamiltonian.